Hello and welcome to our Day 10 lecture for Upward Bound Advanced Math. Today we are looking at the basics of matrices. The first thing I want to look at is the definition of a matrix. A matrix is a rectangular showing of numbers organized into rows and columns. Matrices can be rectangular or square, and when reading the dimensions of a matrix, we do so by rows, by columns. Okay. The example down here is a 2 by 3 matrix. Okay. The rows obviously go this way. These are my 2 rows, and my columns are vertical. So this matrix has 2 rows labeled in blue and 3 columns. So again, we say that this is a 2 by 3 matrix. Okay, and the dimensions are important. The order that we lay those out in is really important. Okay. So let's look at some of the operations that we can do with matrices. Addition and subtraction. How do you think we might add or subtract matrices? Well, it might not really surprise you to think that we do so by entry. Okay, the by entry idea means position by position. Okay, the different numbers within matrices are called their entries. Sometimes you might think of them, or you might hear them as elements, but more standardly it's by entry. You know, each one of these is an entry of the matrix. Okay. So the question is, like this first one, can I do it? Can I add these together? Well, you might think like, well, 1 plus 6 and then 5 plus 5, but then what does 8 get added to? You know, or what adds to this 4 or this 3? And in fact, there is nothing. So because the dimensions don't match up, this sum does not exist. Okay, we would call this one undefined. So a requirement for addition and subtraction of matrices is that we have the same dimensions. Okay, we need the same dimensions. And since here I have a 2 by 3, and sometimes you'll see the dimensions listed on matrices as a subscript. So this would be 2 by 3. This one is 3 by 2. Since those don't match, these cannot be added together. Okay. This one has 3 rows and 2 columns. This one has 2 rows and 3 columns. Since those don't match, there is no sum. It's undefined. Okay. This one can be done because this is a 3 by, sorry, not a 3 by 1, a 1 by 3. And this one is 1 by 3. Since the dimensions match, we can add them together, and it's entry by entry. Okay. So it's what we get here is, and let me back up a second. Since the dimension is 1 by 3 and 1 by 3, the sum will be a matrix that's 1 by 3. Okay, so I'm going to set that up down below. 0 plus -1, -2 plus 3, and 5 plus 0. That's what we're going to get as our sum of these two matrices. So we get a -1, +1, 5. You don't have to do this every time. I think you should be able to just eyeball it and figure out what you're going to get. Okay. Same idea down here, subtraction. It's really the same as addition. We have a 2 by 2 and a 2 by 2. Since they match, they will add or subtract. And that subtraction in this case will give us a 2 by 2 matrix. So if we go ahead and do that, -3 minus 4 is -7. 6 minus 0 is 6. 2 minus -3 is 5. And 3 minus 0 is 3. So that's our answer for that one. Again, this one is a 3 by 2. This one is also 3 by 2. So they will add or subtract, and the result is a 3 by 2 matrix. Sorry. So let's see what that looks like. We are subtracting, so 1 minus 0 is 1. -5 minus 6 is -11. 4 minus -6 is 2. 3 minus -1 is -2. 3 minus -4 is 1. 5 minus -6 is 1. So this is our resulting matrix. Okay, the next thing we'll look at is what we call scalar multiplication, or the scalar product. That's another way to talk about it. And it's just multiplying the same constant to every entry of a matrix. Okay? So we can kind of think of this as sort of like distribution. We're going to multiply the number that's outside by every number inside. This is an operation of matrices that doesn't depend on its dimension. It can always be done unless, yeah, I think it can always be done. So if I multiply this matrix by 2, I'm going to get another 2 by 1 matrix. That's 0, 12. Okay. The next one I'm multiplying by -1/2. It's a 3 by 1 matrix, and it's going to result in a 3 by 1 matrix. Multiplying by -1/2, I get -5, -6.5, and -12. Okay. This one down here gets a little bit ugly. We have a 2 by 3 matrix multiplying every entry by -4. So that'll be 4, 0, -12, and then 8, -20, and 40. Last but not least, we're going to multiply 3 by a 1 by 3 matrix. So my resulting matrix will be 1 by 3, 30, 15, 12. Okay, scalar multiplication is the easier multiplication. When it comes to other operations that we're going to cover in just a second, we will go over matrix multiplication, which is a matrix times another matrix. We can do that sometimes. And then division we don't really do. And I'll talk about that at the end. So I've labeled matrix multiplication as the granddaddy of them all, because it has the most requirements and is typically the thing that takes the longest. I could see the that division, or division I should say, will be the hardest one, but we're not really going to talk about it. We're going to talk about how we could set up a division problem. We're not actually going to divide. So matrix multiplication depends heavily on the dimensions. And for that reason, if I have a matrix that is, we'll say m by n, the only time that I can multiply it by another matrix is if that other matrix is n by m. That's the only time that I can do it. So the key there, actually, I'm going to say, usually those are, usually we talk about a general matrix as being m by n. I'm going to say a by n, and n by b. Those outside two don't have to match up, but the inside two do have to match up. So what that means is the number of columns in the first matrix must match the number of rows. So this is columns, and this is rows. Okay, the number of columns in the first matrix must match the number of rows in the second. And then in addition to that, what you end up with will be a matrix that is A by B, meaning that there are A rows and B columns in your product. Okay? So it's only going to work when these inside, so I always think of these as being the inside two dimensions when they match up. And then to think about what I get as a product, I think of those kind of cancel each other out, and I get the outsides as my new dimensions. So let's go through these four and just see if they're going to work, first of all. Because that's the first thing that I want to check. I want to check, will they multiply? And then I'll go back and figure out how they multiply. This is a 2 by 2. This is a 3 by 2. Since these do not match, this will be undefined, and we don't have to worry about it. This one here is my 3 by 2. And this is a 2 by 2. Since these do match, it will work, and it's going to equal a matrix that is 3 by 2. Okay? Here I have a 3 by 2, 3 rows by 2 columns. And this one has 2 rows by 1 column. Since those match up, they will multiply, and the resulting matrix, I'm not actually showing how big it is going to be 3 by 1. Just sort of planning it out. And this last one is a 3 by 2 and a 2 by 3. So that's going to result in a matrix that is 3 by 3, or a square matrix. Okay, now let's look at how we actually multiply these, because it's not just by entry. Okay, in order to get this first entry, it comes from, let me do it this way. It comes from this row and this column. Okay, what I actually do is I sort of cross multiply. I'm going to multiply the first entry by the first entry in that bubble, and then the subsequent entries by the subsequent entries from this bubble to this bubble, and I add all those together. Okay, let's look at how we can do that, and we're going to use this example right here to drive sort of the definition of this matrix multiplication. So I'm going to take this row and multiply it by this column. And remember, my ending matrix is going to be 3 by 2. So it's going to have 3 rows and 2 columns. So I'm going to take 2 and multiply it by 1. Actually, I'm going to give myself a little bit more room here so I can not do any mental math. So it comes from 2 times 1 plus 5 times 7. Okay, and the way I think about this is as I overlay these two, where they match up, where they sort of match up, if I were to think about putting these two matrices on top of each other, these two circles overlap in the top left. It's kind of the best thing that I can say on how to get there. Okay, now I'm going to think of this same bubble, and we're going to look at this one. Okay, so the red with the green, and that's going to give me my top right. 5 times 5 plus 5 times 3. Okay. Now we will look at the blue and the red. 6 times 1. So 6 times this one, and 1 times 7. Okay, and then the blue with the green is 6 times 5 plus 1 times 3. And then the last one will come from these two, or from this row. 3 times 1. I don't know why I put a 54 there. And 54 times 7. Oh boy. 3 times 5 plus 54 times 3. And that'll be my entire matrix. I'm going to give myself some room. And we'll do some calculations here. 2 times 1 is 2, 5 times 7 is 35, 2 plus 35 is 37. Here we have 25 and 15, which is 40. 6 and 7, which is 13. 30 and 3, which is 33. And here I do need a calculator. 54 times 7 is 378. So that'll be 381. Again, I don't know why I put such a big number there. I think I meant to put either 5 or 4, and it came out with both of them. Let me clean that up a little bit. That's 381. And then I'm going to need that again for 54 times 3, and we'll just add 15 to that, 177. So that's what we get for that matrix multiplication. So you have to think your rows by your columns, go the other way, your rows by your columns, entry by entry, and adding those results together. Okay. That one was sort of a hard example. definitely this last one I think is the hardest of the three that can be multiplied. This one is just going to give me a 3 by 1 matrix, so it shouldn't be too bad. Well, that's 3 rows, 1 column. And I will actually write it out again just to help us one more time. So I'm thinking row by column, -5 times -3 plus 4 times -4. Yeah, I shouldn't have drawn that in there. I regretted it right when I did it. Okay, and then -1 times -3 plus 6 times -4. 2 times -3 plus -2 times -4. Okay. Let's look at what all those entries will be. -5 times -3 is 15. 4 times -4 is -16. So that looks like a -1. -1 times -3 is 3. 6 times -4 is -24. So that's going to be a -21. 2 times -3 is -6. -2 times -4 is 8. So that's going to be 2. So that is our resulting answer for that one. Okay. Now let's look at this one. It's going to give us a 3 by 3 matrix. I'm not going to put that other one in there. And I'm just going to multiply these and kind of talk them out as we go, just to speed it up a little bit. 6 times -1 is -6. -1 times 2 is -2. So that's going to be a -8. 6 times -6 is -36. -1 times 0 is 0. So that's going to be a -36. 6 times 2 is 12. -1 times 1 is -1. So that's a +11. Now for the second row, and so again we kind of see where we're overlapping these two matrices, and sort of that dictates where that goes as far as the entry that falls in. Yeah. Sorry. -2 times -1 is 2. 0 times 2 is 0. So that's a 2. -2 times 6, sorry, -2 times -6 is +12. 0 times 0 is 0. -2 times 2 is -4. 0 times 1 is 0, so -4. Now onto the bottom, and this tells me bottom and far left. -2 times -1 is 2. 2 times 2 is 4, so that's 6. -2 times -6 is 12, and 2 times 0 is 0, so that's another 12. -2 times 2 is -4. 2 times 1 is 2, so that's a -2. And that's what we get from matrix multiplication. Okay. Now we want to look for inverse matrices. Because if we think about inverse numbers, not operations, if I'm looking for the inverse of 4, almost everybody will tell me it's 1 over 4, right? Because that's our rules of exponents. All right, but there's multiple inverses. That would be the multiplicative inverse, or the way to undo multiplying by 4. And that's 1 over 4. But when we think of undoing multiplying by 4, we say divide by 4. That's the same as multiplying by 1/2. And that brings us to the inverse of matrices in the same manner, but we do it a little bit differently. Okay, if I had to undo multiplying a matrix, I wouldn't necessarily try to divide by that matrix. I would try to multiply by its inverse. Okay, so if I'm looking at a matrix and I want to find its inverse, I can only do it under certain circumstances. The most prominent of those is that it must be a square matrix. And that meaning that it's either a 2 by 2 or a 3 by 3. I guess it could be a 1 by 1, but that's not really that much of a matrix as it is just a number. So it must be a square matrix. And we're only going to look at 2 by 2s. Anything above that, you're really wanting to use some sort of calculation device, whether it's a computer, a calculator that can handle it. And even at that, it would take a pretty sophisticated calculator to deal with that level of computing. Okay, so it's not just going to be your run-of-the-mill. I don't have one here. Scientific calculator, and in fact, like this calculator cannot deal with matrices. So I wouldn't be looking at that. A calculator like this could. This is a TI-83 Plus. It has somewhere. Oh, it actually doesn't have a matrix button. And it's dead, so I can't show you anything with that. But it has the ability to deal with matrices. And there's a command in there that you can say, find the inverse, it says raise to the -1 power, or find the inverse of this matrix, and it'll do it. It'll go through all the calculations that we're going to go through really quickly and easily. Okay, but for us to find matrices, again, we're only going to be looking at 2 by 2 matrices. Let me see, for notation. The inverse of a 2 by 2 matrix, and we're going to label the entries for sort of ease of use. We're going to look at trying to find the inverse of matrix A, B, C, D. So this way it doesn't depend on what numbers are in there. We're going to do it very generally. And you do a couple things. First of all, we have to multiply the entire matrix using scalar multiplication. So that was where we just multiply every entry by a certain number, kind of that distributive property. But we multiply it by 1 over what we call the determinant of the matrix. We're calling this matrix A. Okay, it has name A. And so we're finding 1 over the determinant of that. What that actually is, instead of writing determinant there, I'm actually going to write it out because it's easy to find for a 2 by 2 matrix. You get deeper and deeper into matrices, it's a little bit harder. The determinant of this matrix is A times D minus B times C. So we would say AD minus BC. Okay, and that's easy to find for a 2 by 2. The bigger the matrix, the harder that number is to find. Okay. And then, so that's the scalar number. That's the number on the outside of the matrix that we're going to multiply by. We also do some things with the entries of this matrix to sort of turn it into its inverse. The biggest thing about finding an inverse is when we find our inverse and we multiply it by our original thing, or our original matrix, we should get the identity. Typically, we think of the identity as being 1 or 0 in the addition subtraction world. In the matrix world, it looks a little bit different. Okay, and I'll talk about that in just a second. So the way that we're going to mess with these entries is that we're going to flip A and D. So we're going to go D and A. We're going to leave B and C alone, but we're going to make them negative. Okay. Yeah. I don't like that being red. So that will be our inverse of this matrix A, B, C, D. Okay. And again, why that's the inverse is because when you do all that and you multiply it by that A, B, C, D using scalar multiplication, we get this fancy thing. So if I take, and I'm actually going to write out what it is. I'm going to do the scalar multiplication. It's going to make it look a little bit ugly, but if I take, let's use blue. If I take A, B, C, D, and I multiply it by its inverse, which once I do the scalar multiplication in there, looks like this. D over AD minus BC, negative B over AD minus BC, and then negative C over AD minus BC, and down here is A over AD minus BC. So if I multiply those two matrices, yeah, I can't just move that. Okay. But if I multiply those two matrices, it's going to give me what we call the identity matrix of a 2 by 2 matrix. And it's not 1, but it has one, it's a combination of 1s and 0s that has 1s in what we call the main diagonal and 0s everywhere else. Okay? If I take any 2 by 2 matrix and multiply it by this, I'm going to get the same matrix coming out. That's the idea of the identity. Okay? It's the multiplicative identity, and meaning that it doesn't change it. It's like multiplying a number by 1. Okay? So let's try to use this idea right here, and this is the main idea that we want to look at. Let's use this formula for the inverse to find the inverse of these matrices down here. And I only have 2 for us to do, so that's okay. So first thing I want to do is I want to find the determinant, which we said determinant of A, we're just kind of labeling all of our matrices matrix A. We said that it's 1 over, no, it's not 1 over, sorry. It's just A times D minus B times C. Okay? And those A, B's and A, B, C, D, those positions are set right now. So meaning that this is A, this is B, this is C, this is D. So A times D, and that's how this is kind of easily found. You just multiply sort of like cross multiplication. So A times D is 24, and we subtract the other diagonal, 10. So our determinant is 14. Don't ask me why I wrote it backwards. So I will be dividing by 14, or multiplying by 1 over 14. The inverse of this matrix is 1 over 14 times the matrix when we, again, kind of mess with the positions or the signs. We're going to flip A and D, -8 and -3, and we're going to change the signs on B and C, 2 and 5. So our inverse matrix will turn out to be -8 over 14, we could probably call 4/7. Sorry, that's -4/7. 2 over 14 is 1/7. 5 over 14 is just 5 over 14. And -3 over 14 is just -3 over 14. And again, what significance does that have? If I were to take this and multiply it by my original matrix, and in fact in this multiplication it doesn't matter the order, only in this problem. Typical matrix multiplication, the order does matter, but in this case it doesn't matter. That if I multiply this by this matrix, and I'll let you do it just in the interest of time, I'm guaranteed that I'm going to get this matrix back. Oh, that's not right. 1, 0, 0, 1. So that's the significance, that finding this inverse matrix, this main answer here, finding this tells me that that's the matrix that I can multiply by to undo this original matrix. Okay, so that's pretty significant. And we would use that to like solve equations with matrices. If I had to undo multiplying by a matrix, I would have to find its inverse first. Okay, let's do this other problem. Let's find the inverse of this one. So again, I can start off with my determinant. That's my determinant. Multiply these two, -40, minus the product of these two, -35. -40 minus -35 is -5. So that's my determinant. So the inverse is going to be 1 over, maybe we'll just say -1/5, 1 over -5, same kind of thing. Flip A and B, sorry, A and D, and change the signs on B and C. So the inverse becomes, if I do my scalar multiplication, -1/5 times 5 is +1. Again, -1/5 times -5 is +1. -1/5 times -7 is 7/5. And this one will be -8/5. And that is my inverse of that 2 by 2 matrix. We'll put those to use next time when we start solving matrix equations. Okay? But that's the idea of how you would divide matrices, is you would multiply by its inverse, because that's really what division is. And that's why division is overlooked in so many areas, because what you just do is you just multiply by its inverse. Sometimes that's easy to find. In the numbers world, that's easy to find. The inverse of 4 is 1/4. But it's not always as easy. I hope that helps. Make sure you get that homework done, and we will see you in class.